Hello, we're going to go over Chapter 18, Electrochemistry. For the chapter outline, we're going to go over 18.1, which is redox reactions, 18.2, galvanic cells, 18.3, standard reduction potentials, 18.4, thermodynamics of redox reactions, 18.5, the effects of concentration on cell EMF, 18.6 on batteries, 18.7 corrosion, and 18.8 electrolysis.
18.1 Redox reactions. Electrochemistry and redox reactions. Electrochemistry is a part in chemistry that deals with the conversion of electrical energy into chemical energy. It is the oxidation-reduction reaction process. The energy released by spontaneous reaction is converted to electricity, and that electricity can also be used to make a non-spontaneous reaction occur. Redox reactions. They are the electron transfer from one substance to another. Example, here we have an equation where the oxidation is the loss of electrons and reduction is the gain of electrons. So Mg is going to be oxidized and hydrogen ions are reduced. Balancing redox reactions. Here we are going to learn how to balance redox reactions through the ion-electron method. So first, we're going to write the unbalanced equation for the reaction in an ionic form. So that equation is going to be the following. Now our next step is going to divide the overall reaction into two half reactions. So one reaction is going to be for oxidation and the other one is going to be for reduction. So our oxidation is going to look something like this. And the reduction is going to look like the following. Our third step is to balance the atoms other than oxygen and hydrogen in each half reaction. And that is going to be, so we're going to have two reactions, first the oxidation and then the reduction. So the oxidation is, we're going to balance out the atoms by adding the electrons. So your oxidation is going to look like the following. And now you're going to have 2 Fe atoms on the right and on the left. Now the reduction is going to look something like this. Now we're going to go to our fourth step, which is going to be to add water to balance out the oxygen atoms and hydrogen atoms to balance the H atoms for the reactions in an acid. So that is going to look something like this. So you have your reduction equation like this from the previous step. And now since on your left side you have 7 oxygens, then on your right you have to have 7 oxygens. So you're going to have 7 atoms of water, and that's going to be equal to 7 oxygens and 14 hydrogens. Now our fifth step is going to, on one side of each half reaction, add electrons to balance the charges of the half reaction. So it is going to look like this. Cr2. Now, since over here you have 14 hydrogens, which are positive, and you have 2 chromium oxides that are negative, that's going to be 12 electrons, positive charges, and on 12 positive charges on your right, on your left, and you're going to have 6 positive charges on the right. So to balance that out, you're going to have to add 6 electrons to make this, have the equal amount of positive charges, so it's going to be 6 and 6. Now our next step is going to equalize the electrons into half reactions by multiplying the half reactions by the coefficients. So originally we had this reduction equation reaction. So now, and then we had Cr2O7. Now we're going to have to multiply our oxidation equation reaction times 6. So that's going to leave off 6Fe. So now we are ready to get our overall reaction, and the way we're going to do this is through a process of elimination, basically saying that if we have one element or compound on one side and it is found also on the other side, then they both cancel each other out. So we're going to start by looking how many 6 Fe's we have on the right and on the left. So on the left we have 6, but on the right we don't have any, so that doesn't cancel out, and it immediately goes into our overall reaction. Then Cr2O7, we have it on the left but not on the right, so it doesn't cancel out, so you add it. Then you have 14 hydrogens on the left but not on the right, so it goes at the bottom. Then you do have 6 electrons, so those cancel each other out and those don't go at the bottom. Then you have 6 Fe's on your right but not on your left, so it goes at the bottom. Same with your chromiums. And with your 7 waters. So that is going to be your overall reaction.
We will now discuss section 18.2, which is talking about galvanic cells. When explaining oxidizing agents and reducing agents, we typically imagine a situation such as if each of the agents were to be physically separated from each other. In this situation, for example, the transfer of electrons takes place via a conducting wire, while creating a constant flow of electrons and generating electricity. So for example, such situations can be visualized through this process, and zinc would be considered in this process the reducing agent, while copper is the oxidizing agent. So in this process, we can more further explain what a galvanic cell is. A galvanic cell is the experimental apparatus for when generating electricity while using a spontaneous reaction. This word can also otherwise be known as voltaic cell. So we can imagine also a zinc bar being immersed in a zinc sulfate. For example, it would be zinc sulfate, while copper bar being immersed in a copper sulfate. The electrodes in these situations would be zinc and copper, which we would use. And the cell operates on the basis that the oxidation of Zn to Zn2 plus. So for example, this one, the Cn to Cn2 plus, would be the oxidation. So the oxidation in this case would only be involved with zinc. It's going to zinc 2 plus. And we can also see how the cells operates on the base of a reduction, which is for copper. The copper reduction would typically be these two. So the reduction would be copper 2 plus going into copper without an ion. They're both taking place simultaneously with the transfer of electrons through the wire that I previously mentioned. So for the anode, in this case, the zinc and the copper bars are known as electrodes, which I previously mentioned. And the anode in this galvanic cell, this is an example of one, would be zinc. So an anode basically is an electrode that has oxidation occurring to it, and the cathode in this case would be the one that does the reduction, which we mentioned would be the copper. To complete an electric circuit, the solutions must be connected through a medium to allow the cations and the anions to move freely from one compartment to the other, which is called the salt bridge. This is on this diagram before you. This would be one example of the bridge. And then we can involve the cell diagrams. This whole process can have its own cell diagram, which is represented as the above. So in the course for a redox reaction, electrons flow from the anode, which is a zinc. We previously mentioned the zinc right here. The electrons transfer from the anode along the wire to the cathode, which is the copper. And all of this is while the anions move to the anode. So the anion, this is the situation where they all move to the anode, excuse me. The correct way to draw a diagram for the galvanic cell in the salt bridge is through the cell diagrams. This one here, the cell diagrams, such as using the previous situation as an example, which is zinc, and then zinc 2 plus, which is the anodes, with the cathodes separate. So they're both separated, assuming that the concentrations of the copper and zinc of the ions are under the conditions of 1 molarity. The single vertical lines, which symbolize the phase boundaries, whereas the double vertical line symbolizes the salt bridge, which is over here. The anode, in this case, if we were to do the cell diagram, would be written for the first to the far right, always. The anode.
So now we're going to go over 18.3, which is standard reduction potentials. So the Daniell cell's EMF is 1.10 volts at 25 degrees Celsius when the copper 2 plus and the zinc 2 plus ions concentrations are both at 1. The measured EMF of the cell can be treated as the sum of both of the electric potentials of zinc and copper electrodes. So if you were to know one of these electrode potentials, then you would be able to obtain the other one when you subtract 1.10 volts from it. And here's a picture of the cell and the salt bridge. So you cannot measure the potential of a single electrode, but if you were to randomly set a value of a particular electrode as 0, then you could use it to determine the potentials of the other electrodes. So for example, hydrogen gas is bubbled into a hydrochloric acid solution at 25 degrees Celsius, so the platinum electrode then has two functions. And first, it will provide a surface where the dissociation of the hydrogen molecules can take place. So here it is, and then it would also serve as an electrical conductor to the external circuit. So under standard state conditions, when the pressure of hydrogen is 1 atmosphere and the concentration of the hydrochloric acid solution is 1, then the potential for the reduction of hydrogen plus ions at 25 degrees Celsius is exactly 0. So here we can see that the standard reduction potential is 0 volts. So the superscript, this one that looks like a little degree sign, it represents the standard state conditions. So here, E is the standard reduction potential, or the voltage associated with the reduction reaction at an electrode when all the solids are 1 and all gases are 1 atmosphere. So thus the standard reduction potential of the hydrogen electrode is defined as 0, and the hydrogen electrode is called the standard hydrogen electrode, also known as She, and She can be used to measure the potentials of other kinds of electrodes. So by convention, the standard EMF of the cell is composed of a contribution from the anode and from the cathode, and is given here by the standard reduction potential equals the potential of the cathode minus the potential of the anode, where both the cathode and the anode are the standard reduction potentials of the electrodes. And here for delta G, we can use the sign of the standard reduction potential to predict the extent of a redox reaction. And a positive E means the redox reaction will favor the formation of the product at equilibrium, but a negative means that more reactants than products are formed at equilibrium. So then here we have the table that is included in our chapter, and this is the table of standard reduction potentials at 25 degrees Celsius, where the She has a value of 0 volts. And as you go down the table, you are more likely to be oxidized, and it is a better reducing agent. But if you were to go up when it's more positive, then it's more likely to be reduced, and it is a better oxidizing agent. So it just depends on if you go down or if you go up, like if it's going to be oxidized or reduced. So if you go down, you're going to be a better reducing agent. If you go up, you will be a better oxidizing agent. So there are important notes to keep in mind when you're looking at the table. So if the standard values apply to the half cell reactions as read in the forward direction from left to right, and the more positive E is, the greater the tendency for the substance to be reduced is going to be. And the half cell reactions are reversible, so depending on the conditions, any electrode can act either as an anode or as a cathode as well. Under standard state conditions, any species on the left of a given half cell reaction will react spontaneously with the species that appears on the right of any half cell reaction located below, or located in the table, sorry. So this principle is sometimes called the diagonal rule. And so changing the stoichiometric coefficients of a half cell reaction does not affect the value of E because electrode potentials are intensive properties. So this means that the value of E is unaffected by the size of the electrodes or the amount of solutions that are present. So similar to these changes, the sign of E changes, but its magnitude will remain the same when the reaction is to be reversed. So now we're going to go over 18.4, which is the thermodynamics of redox reactions. So in a galvanic cell, the chemical energy is converted to electrical energy to do electrical work, for example, like running an electric motor. And electrical energy in this case is the product of the EMF of the cell and the total electrical charge in coulombs that passes through the cell, which is represented by electric energy equals coulombs times volts, which will equal U to joules, meaning that 1 joule equals 1 coulomb times 1 volt. So the total charge is determined by the number of electrons that pass through the cell. So we have then total charge equals number of electrons times the charge of one electron. So the charge of 1 mole of electrons is called the Faraday constant, or F, and it is named after the English chemist and physicist Michael Faraday, where 1F equals Avogadro's number times 10 to the negative 19th power, which will equal 9.647 times 10 to the 4th power. So the total charge can now be expressed as an F, where the N is the number of moles of electrons exchanged between the oxidizing agent and the reducing agent, and in the overall redox equation for the electrochemical process. So the measured M for the E cell is the maximum voltage that the cell can achieve. Maximum voltage. So therefore, the electric work that is done, so the microstates electric, which is the maximum work that can be done, or the mass, is given by the product of the total charge and the nth of the cell. So here we have the equation where the maximum is going to be the electric, which is equal to NFE of the cell. So this negative sign shows that the electrical work is done by the system on the surroundings. Or the system would also be the galvanic cell. So the change in free energy, or delta G, represents the maximum amount of useful work that can be obtained in a reaction. So the free energy will equal the maximum amount of work done by, which is equals the electric work. So therefore we can write delta G equals NFE cell. And for a spontaneous reaction, delta G will be negative because NF and NF are both positive quantities. It follows that the E cell must also be positive. So reactions in which the reactants and products are in their standard states, so 1M or 1 atmosphere, then the equation is delta G equals NFE standard state of cell. When solving for E cell, we can use E cell equals RT divided by NF multiplied by the natural log of K. And this equation can be simplified when you substitute R and F values when the temperature is equal to 298 kelvins. Then the equation would then read 8.314 for the R and then 298 for the temperature, and you divide it by the F constant of 96,500. Or it could also be simplified to E cell equals 0.0257 volts divided by the number of moles times the natural log of K. But if the base was to be 10 logarithm of K instead of the natural log, then it would be E cell equals 0.0592 volts divided by number of moles times by the base 10 logarithm of K. And then here we have a table from 18.2, which is the relationships among the delta G, K, and the E cell. So it shows you that when delta G is negative and then K is less than 1, then the E cell is positive and will favor formation of products. Whereas then if delta G was 0 and K was equal to 1, then E cell would also be 0, and the reactants and the products are actually equally favored. But if delta G was to be positive and K was to be greater than 1, then the E cell is negative and would favor the formation of the reactants.
So there's this equation called a Nernst equation. It's basically a mathematical relationship between the EMF of the galvanic cell and the concentration of reactants of the product in a redox reaction that are under a non-standard state. So remember, in order for this equation to take place and for it to work and everything, it has to be under a non-standard state. It's very important part of the equation of all this to work. So this equation it can be expressed as, or you can use this equation what's it called? I have it right here, annotated right here. This equation is something very important. As soon as you get all the numbers and everything, you just plug it into this equation and you can use the Nernst equation basically. So this is this operation is basically simple. It's not that well. It's negative n times f times e equals negative n times f times e plus the r times l and the natural logarithm in q. So not that hard. It's kind of complicated, but still, it's manageable and everything. In the operation of the galvanic cell, the electrons will flow from the anode to a cathode. That's a very important part of this equation to understand where the electrons are flowing from what side to what side, from a direction to one direction, okay? So remember, always have in mind and always keep it in mind that whenever this equation or operation, if you want to call it, is in equilibrium, E is always going to equal to 0, Q is always going to equal to K, and remember that K is the equilibrium constant. Okay, that's something to have in mind. So the Nernst equation enables us to calculate E as a reactant and product concentration in a redox reaction. So remember we said that E equal to 0 in equilibrium. Well, with this Nernst equation, we're going to be able to find E and look for it. So, concentration cells. Concentration cells are pretty important in this too. So a concentration cell is possible. It is possible to construct a galvanic cell from the half cells composed of the same material, but different in iron concentration. So a cell, basically, this is the definition of a concentration cell. Okay, so according to Le Chatelier's principle, the tendency for the reduction will increase with an increase of concentration of Cn plus 2 ions in the equation right here that I have as an example. Ooh, the little arrow moved a little, but a little arrow is supposed to go right here in the middle of this. There we go. So basically by increasing concentration of Cn2 plus ions, this would cause for the reduction to occur in the more concentrated side, and the oxidation will occur in the more dilated side. So keep that in mind, that concentration is always going to go, reduction is always going to occur in the more concentrated side, and oxidation will occur in the more dilated side.
Batteries. Batteries. A battery is a galvanic cell, or many galvanic cells use electric current at a constant voltage. It has complete features, therefore there is no need for salt bridges. There are different types of batteries. The first one would be the dry cell battery, then the mercury battery, the lead storage battery, the lithium-ion battery, and fuel cells. The dry cell battery. It is the most common dry cell. There is no fluid component, and it is used in flashlights and transistors radios. The anode, it is a zinc can that is in contact with manganese oxide and an electrolyte. The electrolyte is the ammonium chloride and a zinc chloride all in water, and starch is added to thicken the solution. So here, then the cathode is the carbon rod. So here you have your anode and your cathode. And these would be your oxidation reduction reactions, and the way you get your overall reaction as seen as in section 18.1 is that if you have one element on the other side and one element on the right and the other one on the left, then they cancel each other out. So I'm going to show you how to do the process of this. So we're going to start off by seeing that we have zinc on the left but not on the right, so it goes at the bottom. Then 2NH4 is on the left but not on the right, so it doesn't cancel. 2 manganese oxides, you have them on the left but not on the right, so they go at the bottom. Then you have a zinc on the right but not on the left, so it goes down. Then we see here that we have 2 electrons. One is found on the left and one is found on the right, so they're going to cancel each other out. Then you have your Mn2O3s, and that's going to go at the bottom. Then you have 2 NH3s, that goes at the bottom too. Then you have your waters, and that goes at the bottom too because it doesn't have another same compound to cancel it out, so that's going to be your overall reaction. Now we're going to jump into the mercury battery. It is a constant voltage of 1.35 Vs. It has a higher capacity and a longer life. The anode is a zinc in contact with the alkaline electrolyte, which contains zinc oxide and mercury oxide. It is used in medicine such as pacemakers and hearing aids, the electronic industries, and electric watches and light meters. So here you have your anode, your cathode, and your overall reaction. Now we have the lead storage battery. The anode is the lead in an aqueous solution of sulfuric acid. Your cathode is the lead oxide in an aqueous solution of sulfuric acid. Here you have your anode, your cathode, and that's how you get your overall reaction. And lead storage battery is also used in automobiles, which have 6 cells, which means you have 12 voltages and they are rechargeable. Your lithium ion battery, it is the anode of the carbonaceous materials such as graphite. Your cathode is the transition metal oxide. It is used in cell phones, digital cameras, and laptop computers, meaning that they are rechargeable. It is the most negative standard reduction and has the greatest reducing strength. We have your anode with the lithium and your cathode, and this would be your overall reaction right here at the bottom. Then you have your fuel cells, which are a galvanic cell that requires various reactants to keep its function. The standard EMF of a cell. So the equation for that would be the following. The EO of your cell equaling the EO of the cathode minus the EO of the anode. So let's say, for example, your cathode is 0.40 voltages and your anode is negative 0.83 voltages. Then your overall EO of the cell is going to be 1.23 voltages. So the cell reaction is going to be spontaneous. You have your anode, your cathode, and your overall reaction.
So section 18.7 of chapter 18. On this section, we'll be looking at corrosion. So corrosion may sound like a chemical term or something, but it's just a little name that scientists decided to give a normal thing that everybody has seen in their life. Literally, corrosion, you can see it taking place everywhere you go, almost everywhere you go. You can see it in your garage, you can see it in your backyard, you can see it outside, you can see it on buildings and cars and ships and almost anything. And metals, copper, silver, all those things have corrosion in it as time goes by. So corrosion is usually used to describe the deterioration of metals by an electrochemical process. But this electrochemical process is basically something where it reacts and creates a product that affects the shape, texture, or even the element that's in. So basically, almost like this, corrosion, you can basically in rusting of an iron. You can see how the iron changes color, it changes texture, it becomes more fragile, and that's how corrosion is happening. That's exactly corrosion, the rusting of an iron. So remember that due to corrosion being a diffusion control process, it occurs on exposed surfaces. It will rarely never occur inside of the object. So basically on a nail, if it's rusting and you take it and cut it in half, you can see in the inside that rusting is not happening in the inside, but the rusting is actually helping um is occurring outside of the nail. So it really basically only takes place on the exposed surfaces that it's exposing to a certain chemical, certain to air, to water, or a certain type of element or something. So corrosion is something big here in the United States, because like I was mentioning, it affects building, cars, bridges, ships, and everything. Basically, almost that has metal. Everything that has metal, it affects. So it's something really common here in the United States due to it affecting the United States economy by costing about $200 billion dollars to repair all of the corrosion that's happening, and that's just, we really don't see it. We just see, oh, it's rusting, oh, look, that nail is rusting, oh, the building is rusting or something, but it's really something so normal that we think it's not a big deal, but it's happening all over the United States. So corrosion is nothing new to us or nothing. We're just seeing it as a chemical version, as a reaction that's happening. That's it. So some examples, like I was saying, the rusting of an iron on iron and everything, the tarnish on silver, and the green patina formed on copper and brass. Those are some examples of corrosion and everything. So it's nothing big, like I said. Well, it's just the normal things. Okay? Corrosion, just look at it as a chemical reaction that's happening, that it's affecting the texture, color, and the itself, basically.
For the final section, we'll go over section 18.8, which is electrolysis. To further explain, electrolysis is basically a process where electric energy is used in order to cause a non-spontaneous chemical reaction to occur. There are special methods to carry out the electrolysis, one being by using an electrolytic cell. An electrolytic cell is a specific apparatus that allows for carrying out electrolytes. I will further explain what an electrolysis is with three different examples showing what exactly electrolysis is. So for the first example, we will be using electrolysis of a molten sodium chloride. In molten sodium chloride, the cations and anions would correspond to sodium and also chlorine. The present diagram below, it shows the reaction that occurs at these electrodes. The diagram shows electrolytic cells that have pairs of electrons that connect to a voltage source. But in this case, it would be a battery. So the voltage source is connected, we would consider that as a battery. That would be the example for the process, the battery, which is responsible to drive electrons to the cathodes where reduction happens, and also it is responsible for withdrawing electrodes from the anodes. So it withdraws electrons from the anodes, the battery withdraws, and it also drives the electrons to the cathodes. So as the electrons move up, they go down as well for the cathode. For the overall process seen as above, voltage would be -4. So the overall voltage would be -4, meaning that it is non-spontaneous, which relates to the minimum amount needed to supply the battery for it to work. So for example, as I previously mentioned, there would be -4 voltage. So this is 4 volts is what's needed to make the battery itself do the whole process of it, driving the electrons and also withdrawing the electrons. So for another example in electrolysis in water, is electrolysis in water, which is water under the conditions of 1 atmosphere at 25 degrees Celsius, spontaneously dissolve into hydrogen and oxygen. So for gas, because the standard free energy is positive. So in this case, the electrolysis of water is cannot be spontaneously dissolved into those 2 hydrogens and oxygens, like if one is wanting to. because the standard free energy is positive. So this would be the standard free energy process of water. Since it's positive, it won't be able to be moved spontaneously. If we were to show you the more standard free energy example, this reaction is capable of being induced into a cell with the help of the solution. So it can be changed into a cell only with the solution of 0.1 molarity of sulfuric acid. This is due to the fact that this solution has enough ions to conduct the electricity that is needed for the whole process to begin. Another example, which is the final example of electrolysis, is electrolysis of an aqueous sodium chloride solution. So this is the most complicated of the three because the sodium chloride solution has species that can be oxidized and reduced as well, both ways. This reaction of oxidation that can happen as the anodes are represented as these two equations. So this is 1 and this is 2. For chloride and for water, the values of 1 and 2 simply imply that water, or H2O, should be oxidized as the anode. So the H2O, this is H2O, should be oxidized as the anode. But if we were to do an experiment, we find that the gas liberated, this gas liberated at the anode is, instead of O2, is actually Cl2. So Cl2, if we were to do an experimentation, would be the ending result. But in this case, it would be O2. So there must be a problem with that. This is the problem involved, is over voltage. Let me resolve that. Over voltage. So that's the difference between the electrode potentials and the actual voltage that is required in this process. Because of the over voltage of O2 gas, it is too high, which makes sense that Cl2 is formed at the anode instead. So the quantitative aspects of this whole electrolysis processing is best explained overall as measuring the currents in amperes that pass through an electrolytic cell in a certain time period. It can be seen as the following equation. So the 1C would be the current, and it's 1 times the amperes times 1 second. This is the time measured, and these are the amperes.